Okay, let's take a look at this exercise where we're going to calculate the stopping distance of a car. So we have a car kind of on a level surface here, even if my line isn't level there. And we have, here it is, and it's an 1800 kilogram car. And it's traveling along at some initial velocity. I believe they give us here at 23 meters per second. So it's kind of cruising along here. Call this V naught, or actually I'm going to call this position 1. So this will be V1 is 23 meters per second. And then, the driver slams on the brakes and the car comes over here and skids to a rest, right? And so now this final velocity, and we'll call this V2, is equal to 0. So we have here, this is kind of like, this is our position 1, and this is position 2, which is the way that we typically will apply work energy theorem or conservation of energy exercises here. So position 1 and position 2. And really what the work energy theorem does is it takes Newton's second law and kinematics and blends them together really nicely to solve it more succinctly, and really we can take much more complicated problems and solve them with conservation of energy or the work energy theorem than we could with just Newton's laws and kinematics. We're also given some other information here. We have this coefficient of kinetic friction is equal to 0.70, and yeah, we want to find out how far it travels. Now, we can do this with just Newton's laws and kinematics. If I take a free body diagram of it, as it is over here in position 1, and I give a coordinate system, positive y up like this, positive x this way, and then I look at the forces acting on it, we have a weight going down like this, 1800 g, we have a normal force up like this, and then we'll have a frictional force when we slam on the brakes like this. We have the weight, we have the coefficient of friction. We can find, the normal force because there's no acceleration in the y direction. We can find the frictional force. We have a mass. From here we can get an acceleration, and then we can apply kinematics. And I encourage you to do that because our exam will cover Newton's laws, kinematics, well, Newton's laws, and could be some kinematics built into it, as well as work energy theorem here. So try to solve it with Newton's laws and kinematics, and then also try to solve it with the work energy theorem like we're going to solve it here now. So the work energy theorem says that the work done on an object, so we'll say the work done on the car by all the forces, so the work done on the car is equal to the change in the mechanical energy of the car, right? We can simplify this down a little bit based on just what we have here, what we see. There's no height change, right? So we have kind of, this delta H is equal to 0. So we have gravitational potential energy is related to a height difference, right? But there's no height change, so there's no change in potential energy. There's no change in gravitational potential energy. There's also no springs, so we don't have any change in elastic potential energy either. The only thing that we're going to have a change in is our kinetic energy, right? We have some speed here and then, a different speed there, namely 0. So really we have a change in just in kinetic energy is actually what this boils down to for this problem here. So the change in the kinetic energy of the car. And we also say, the work done on the car. Well, the displacement is in this positive x direction, right? So S is in this positive x direction. So I know that the normal force doesn't do any work and the weight doesn't do any work, right? Neither of these do any work because there's no displacement in either of those directions. So the friction is the only thing doing any work, right? So what we can say here, just by taking a look at what's going on in our figure with the car and the two conditions there, position 1 and position 2, we know that the work done by friction, on the car is equal to the change in the kinetic energy of the car. Okay, this is what we observed just from the scenario, from the situation, right? So in order to find this frictional force, or the work done by friction, we need the frictional force and we need to know the displacement, right? Well, the frictional force we can find, because we need the normal force and we need the coefficient of kinetic friction. So summing the forces in the vertical direction, we can see here, since the acceleration in the y direction is equal to 0, we have the sum of the forces and the y direction is equal to 0, and it should be fairly obvious here that we'll end up with the normal force is equal to the weight. Frictional force is the coefficient of friction times the normal force, right? So we get the frictional force, the magnitude of the frictional force, is equal to the coefficient of kinetic friction times the weight, mu k mg. And I know the direction of the frictional force is actually negative, so I could say that there. And the displacement is what I'm looking for. Call this S. And this is getting a little bit messy here. So let me kind of clean that up. I have some displacement, whatever it ends up with. Oh, actually, I kind of drew it ending up over there. Use a different color. This is where it ends up, right? So this is my displacement, S. Okay, so this frictional force times this displacement is the work done by friction, which is equal to the change in the kinetic energy. So we have negative mu k mg s is equal to, right, this is my frictional force, this is the direction of it, this is the displacement, and this is equal to the change in the kinetic energy. Well, this is going to be the kinetic energy at, remember, change is always final minus initial, so this is the kinetic energy at position 2 minus the kinetic energy at position 1, right? So I can expand this out. I can say this is equal to, this is 1/2 mv2 squared minus 1/2 mv1 squared, right? Which actually I can factor out of 1/2 m, and well, but I don't necessarily need to, because actually we end up with v2 is equal to 0 because it comes to rest. Maybe if it didn't come to rest, it might be a little bit more convenient to go ahead and factor out that 1/2 m, but it comes to rest, so we have v2 is 0, so this whole thing disappears. So we have negative mu k mgs is equal to negative 1/2 mv squared. So we have a mass on both sides, which actually cancels out here, right? And we have this S, and this was, by the way, this was V1, right? The negatives also cancel out here. And just solving this, we end up with S is equal to, this is V1 squared over 2 mu k g, which you'll actually, if you do Newton's laws in kinematics and you leave it algebraic instead of plugging in numbers, you will get exactly this. So I encourage you to do that on your own. Or actually, you'll probably call it delta x, using the kinematics, but it's the same thing as the displacement. So now plugging this stuff in, we have, this is V1 was 23 squared divided by 2 times 0.7 times 9.8. And we end up with this displacement here is 38.56 meters. That's how far it travels. This might seem a little bit longer at first using the work energy theorem, but we wrote out a lot of the steps here. you still have to do a free body diagram. You still have to get your frictional force. So you can't really fully get away from that. But if you practice this, the work energy theorem in many cases, most cases, is simpler than using Newton's laws and then kinematics. There's a part B to this that says how far would the car travel if we're going twice as fast? And this is where energy analysis, aka the work energy theorem, really shines. So in part B, what happens if our speed goes to twice the speed, right? Well, I mean, I have this kind of nice little thing here. What happens to my distance if I double the speed? Well, I look at it here and I say, all right, go to 2v, but it's not 2 times v squared. The whole thing has to be squared, right? So this would be equal to, this would come out to, once I square that 2, now I have 4 v1 squared over 2 mu kg, right? So that's 4 times what I originally had because the speed gets squared. So if the speed goes to twice the speed, then the distance goes to 4 times the distance. And so I would just have for part B, my displacement here is going to be 4 times 38.56, whatever, that's like 154 meters. Okay, so if you double the speed, you can actually look at it just in the work energy theorem. We say that the work done, which is a parallel force applied through a displacement, is equal to the change in, if it's just kinetic energy here, change in 1/2 mv squared, right? So if I have twice the speed, I have 4 times the energy. And so I have to do 4 times as much work. There's no way around that in order to stop it, right? Everything else being equal. If I have twice the energy, or twice the speed, I have 4 times the energy, and therefore I have to do 4 times as much work. I can't increase the force by 4 times, not without either increasing the coefficient of friction or the normal force, right? I can't make the car heavier, and I can't change the way the surfaces interact. So the only thing I can really change is how far it travels, right? The distance which this work is done over. So by doubling the speed, quadrupling the energy, quadrupling the work, quadrupling the distance. So I'd have to go 4 times as far. And this is why, you have like the fines double in school zones, right? If you go twice as fast, then you're going to skid a lot farther, right? And it's a much more dangerous than, it's not linear. It's exponential, right? Your distance, you're going to slide there. So yeah, I mean, if I was going 3 times as fast, if you're going 3 times the speed, then you have 9 times the distance to stop, right? Yeah. So this is proportional reasoning, and it really, you can see it much more clearly in energy analysis than you can in Newton's laws and kinematics, I think. Part C asks, what happened to the original kinetic energy? So where did this original kinetic energy go? Well, energy is always conserved, right? So energy doesn't disappear. We can't just say, oh, energy disappeared. Mechanical energy is not always conserved, right? Mechanical energy, we just have a couple, type forms of energy, which we call mechanical. Kinetic energy is one of them. So we actually lose mechanical energy here, right? Because we can't get it back. And so it's kind of goes into heating the tires, right? Because slam on the brakes, your tires up against the roadway, they heat up. But there's other things as well. You could have deformation of the tires if little chunks of rubber were to come off. You could have sound, right? Sound is energy, and so you have sound generated there as well. But most of it goes into just heating up the rubber in the rubber and the roadway. Both of them get heated up a little bit. But energy is conserved. Kinetic or mechanical energy, not so much, but energy is.